Yeah, it's okay.
Okay. And now you should see the full screen.
Yeah, it's okay.
Okay. So thank you for the possibility to give this lecture. This lecture will be on error estimation in vector network analyzer, and in particular, the errors when we measure permittivity. And uh, the general idea in permittivity measurement is basically to use a sample that is placed in a controlled device. In this case, is a waveguide, and we measure some quantities that are usually the reflection coefficient or transmission coefficient, and from the measurements we estimate the permittivity. So the method is, at least theoretically, quite simple. And it's basically an inverse problem. We know the relationship between the reflection coefficient in this sample and the permittivity of the material, and we estimate the permittivity from the measurements. And as any inverse problem, the key, the secret, let us say, of the method is to have accurate measurements. Uh, no mathematical trick in some way can substitute good measurements. And we are lucky because there is a device that is the vector network analyzer that is able to measure transmission and reflection coefficient with very high accuracy. And the idea is this is the network, an example of network analyzer. And before discussing network analyzer, I want just to recall how we model a microwave device at microwave frequency. This is a two-port microwave device, and we have the wave that enters into the port 1 and the wave that goes out from the port 1. And on the other side, we have a wave that goes outside the port 2 and a wave that goes inside the port 2. And we have generally different input impedance. This device is linear, so we can represent this device using a matrix, and this is called the diffusion matrix. And in measurement, we use a generalized diffusion matrix in the sense that instead of considering the voltage, we consider a quantity that is proportional to the voltage wave. This quantity are this B and this A. A is proportional to the voltage wave that goes inside the device, normalized by the input impedance. And B is instead proportional to the voltage that goes outside, normalized to the input impedance. Basically, what we have in this matrix are two reflection coefficient S11 and S22, and two transmission coefficient S21 and S12. And by this matrix, we are able to characterize this device at microwave frequency. So when we talk about S parameters, we talk about reflection or transmission parameters. And this is basically a measurement of reflection or transmission measurements. And this is the vector network analyzer. What I want to stress is that we measure these quantities inside the vector analyzer. When I, for example, when I measure the reflection coefficient, what I measure is the ratio between this signal A, that is the signal that goes from the source of the vector network analyzer reaches the device under test and then is reflected and reaches the receiving part of the vector analyzer. What I mean is that what we measure at the measurement section of the vector analyzer is not exactly what I want, that is the reflection coefficient at this section, because we have all these devices between the real measurement section of the vector analyzer and the section where I want I want the reflection coefficient. So this means that when I measure these quantities, I make a mistake, an error. And so this error is given by all the reflection and transmission and all the complex stuffs that are between the real measurement section of the VNA and the measurement section where we want to know the reflection coefficient in this case. Of course, the same is true for the transmission coefficient. What I measure is something at this section. What I would like is something at this section. How to solve this? Well, first of all, we can model all the stuffs that are between the true measurement section and the measurement section where we want to know the reflection coefficient in this case, using this model, this S model. So in this case, A1 is basically this R, B1 is basically this A, and everything is between all this stuff and the DUT is modeled using this S matrix. So the S matrix models everything there is between the true measurement section and the measurement section where I want to know the reflection coefficient. And this is what happens in practice. This is the incident wave, and then this models all the devices that are between the measurement section and the load. And what I have is that this is the signal from the generator of the vector network analyzer. We have here in this equivalent device a port, and this means we have a first reflection from this port. The signal goes on, it reaches the load, and it's reflected by the load. And in this case, in this reflection, we have the information that I want, that is the reflection coefficient of the load. This signal goes on, then it arrives to this other port of this equivalent error device. We have another reflection, and part of the signals goes through this equivalent device and, arrives to the receiving section. So this means that at the receiving section, we have the interference between this signal and this signal. Then it goes on, we have other reflection between this port 2 and the load, and part of the signal goes on. We have also this other signal, and so on. So at the receiving section, the true receiving section of the vector network analyzer, we do not have only GAM-L, but we have the interference between all these signals, S11A1, S12, S21, gamma-L A1, and so on. And gamma-L is embedded inside all these signals. So at the receiving section, I have the sum, but this is a series because we have an infinite number of reflections between this port and the load. so that what I really receive with the VNA is this series. That can be, of course, closed, and this means that the ratio between what I receive and the reflected signal and the incident signal, and this is a reflection coefficient at the measurement section, true measurement section of the VNA, is not gamma L, but is this much more complex quantity. And it depends also on these S parameters of the equivalent circuit that models everything there is between the measurement section and the load section. Of course, all these other contributions, the third, fourth, and so on, are quite small because they depend on higher reflections. So at first order, what I measure is S11A1 plus this quantity. This is the reflection coefficient at the first order that I measure. And inside this, there is gamma L, that is the quantity on which I'm interested. So, of course, the S parameters are the parameters of an equivalent, let us say, error device. So in literature, they are not called S because we use S for the device under test usually. So they are used E. E stands for error because they are related to a error circuit. And S11 is called the directivity error. S12 multiplies S21 is called the reflection tracking error, and S22 is called the source match error. These are the names that you will find on the literature on VNA. And this is a scheme of a graph of the signal. The signal in practice finds a first reflection at the first port, and this is due to ED. Then it goes on through this equivalent error circuit. It reaches the load gamma L, then it's reflected. Part is again reflected due to the presence of the second port of the equivalent error circuit. This is ES and comes back. And here we have a loop. And another part comes to B1. What the vector network analyze measure is the ratio between B1 and A1. I will call this gamma M, the measured reflection coefficient. Instead, the reflection coefficient of the load is called gamma L. Of course, what we want is not gamma M, but gamma L. And this is the expression of gamma L as function of gamma M, of a function of gamma L, when we expand this formula and we stop at the second order, gamma L squared. Sorry. So each of these terms are really interesting for analyzing the error that I have at the end of the measurement. I cannot enter into the details of all these terms. I want just to spend a few words on this term, ED, the effective directivity. So let us suppose that ER and ES can be negligible. And so what I measure with my vector network device is equal to gamma L, that is the quantity that I want, the reflection coefficient of the load, plus this directivity error. So what I have is the interference between two signals. One is ED and the other is gamma L. And for example, let us consider a measurement of a load. I can use a cable, and the cable is connected to the load using a connector. And you can buy a connector for 50 cents or connectors that cost several hundred euros. What is the difference between these connectors? The difference is the reflection coefficient of the connector. Let us suppose that we want to measure a load whose reflection coefficient is very, very low, okay? And we use a connector whose reflection coefficient is not so low. For example, the load is 40 dB, and the reflection of the connector is 20 dB. In this case, what I have is that at the end, what I measure is not gamma L, but is ED. The signal that I measure is just the reflection of the connector. This means that if I want to measure very low loads, I need connectors that must have very low reflection coefficients. Otherwise, of course, I'm not able to measure the load. I measure the connector. Sorry, there is a minus. Cancel this minus. It's a typo. Okay. Then we have the other errors. Each of them causes an error, of course, in the final measurements. So at the end, what I have is this quantity that is gamma L, M, while I want gamma L. How to solve this problem? Well, we have a relationship, so we can invert this relationship and we can estimate gamma L from gamma M. This is possible provided that we know ED, ER, and ES. And so the next step is how to evaluate these equivalent error parameters. And the solution is to measure some known loads. One of the most common method is to use three loads. One is a short circuit, and in this case, the measured quantity when we use an ideal short circuit is equal to this formula. Then we can use an open circuit, and we have a second equation. Then we have a matched load, and we have a third equation. If the load is perfectly matched, the reflection coefficient is just the error directivity. And from these quantities, we can invert them. We can evaluate ED, ER, and ES. And from these quantities, we can estimate gamma L. And this is basically the procedure that is used in a vector network analyzer. It's understood that I have to know the loads with a very high accuracy. Any error in the knowledge of the load gives an error in the evaluation of gamma L. This means that we need extremely precise loads. Okay, we have a number of standard methods for estimation of these parameters, but in many cases we can think a bit about in order to obtain some methods that can work better than standard methods. I want to show you an example of this. This is a truncated coaxial cable. It's a very commonly used method for liquids, and the idea is to use a coaxial cable that is cut at this section. We measure the reflection coefficient at this section, and in this way, by measuring the reflection coefficient, we are able to estimate the permittivity of a liquid inside which the tip of the coaxial cable is inserted. And the standard way is to use an open-in air, then a short circuit. That means that I close the tip of the coaxial cable with a short circuit, and then we use a reference liquid. That is a liquid that we know. It means that we know the permittivity of this liquid. We can estimate we can measure, of course, the reflection coefficient, and from this we can estimate the error parameters. And of course, this method works. The problem is the reference liquid, because we must know the permittivity of the reference liquid with a very high precision. And this is quite complex, first of all, because we need an extremely poor reference liquid. And furthermore, the permittivity depends on the temperature. So the accuracy is limited, and this limits the accuracy of the final measurement. In order to overcome this, we can, let us say, face the problem according to how we face the inverse problem. We can use the information on which we trust the most. And a possible information is the dispersion law of the liquid. And the most part of the reference liquids have a dispersion law that is basically this. We have, it's a standard dispersion law. We have also this parameter to have another degree of freedom. And of course, this is the frequency, so we must measure the reflection coefficient in a large band, and X are some unknowns. These unknowns are epsilon infinite, epsilon 0, tau, and alpha. So these X are the unknown of our, let us say, inverse problem. Of course, we know this quantity, epsilon 1, epsilon 0, tau, alpha, and so the vector X, with a quite good accuracy, because we use some reference liquids. So the goal of the problem is not to find X without any knowledge of this quantity, but to, let us say, improve our knowledge of X. We have some starting points for X, that a starting point that is very good. We want to improve this in order to take into account the uncertainty, let us say, that we have on the liquid. And for example, we can use an open-in air, a short circuit, and a first liquid that we partially know. That means that we know the permittivity. We want to improve in some way the knowledge of the permittivity compared to the standard value. And we can use these three measurements to estimate, for example, the parameter ED. We can estimate all the three parameters. Let us suppose that we estimate ED. Of course, ED is still a function of X. X is the unknown parameter, are the unknown parameters. Then we can use a second partially non-liquid. And we can again use opening air, short circuit, and this second partially non-liquid to estimate again E. Of course, this E is a function of the unknown parameters that are generally different because these are two liquids. But the error circuit is the same. The error circuit is everything there is between the section of measurement of VNA and the tip of the coaxial cable. So we must have the same E for the two measurements. And so we can find the intersection point, and this intersection point is the value of ED. And from ED, of course, we can then estimate ER, ES, and so on. And this is another possible way to calibrate the network analyzer in this case. This is just an example. We used ethanol and methanol, not perfectly pure in this case, and we reconstruct the water, the distilled water, and well, this is what we obtain when we use the, let us say, two liquids calibration. We have a better performance compared to the use of only one liquid. This is just an example on how the calibration methods can be in some way optimized for our goal. We use this the coaxial cable, truncated coaxial cable, for a lot of application. This is, for example, the characterization of polymers and composites. This is the polyethylene glycol. And we reconstruct the dispersion law as function of the molecular weight and as function of the temperature. These measurements, permittivity measurements, are particularly useful for, of course, numerical simulations. For example, we analyze the cure of epoxy resins, and this requires the knowledge of the permittivity as function of the temperature and a function of the cure state, that is alpha in this case. And these are some example of the results. D is the thickness of the device. What we want is that the temperature and also the cure is as uniform as possible in the sample, and in this way we can in some way optimize the cure of the resins. I want just to show some other example of permittivity measurements and their applications. This is an application in hyperthermia. In this case, the goal is to increase the temperature of the tissue, human tissue, in a, of course, controlled way. And we use permittivity measurements to simulate muscle tissue. This is an example of a simulation of temperature distribution in the tissue, and this is a measurement using a thermochamber in a phantom, and in this way we use the permittivity of the tissues measured as function of the temperature in order to obtain some numerical simulation of the increase of the temperature. This is another application. This is the application for the red palm weevil pest control that in Italy, and not only in Italy, in all the Mediterranean area, has been and is a really great problem, because almost a huge number of palms have been destroyed. And in this case, the idea is to increase the temperature using microwave, and to reach let us say, the killing temperature for the insect, without reaching the killing temperature for the palm. And this is one of the devices that we built. These are microwave. These are basically microwave ovens. A lot of microwave ovens around the palm. This is an example of increased temperature. The problem is how to control the temperature, and this requires the knowledge of the permittivity of all the stuffs that are involved in the microwave heating, that is the palm and also the insect, and the palm in different studies, as well as the insect, adult, larva, and so on, as function again of temperature. And this is, for example, some examples of temperature. These are simulated values using a model based on the permittivity measurement, of course. And these are some measured data. These are triangles and square and circles. And in this case, we had some good results. We checked the method, and we had a quite good rate of killing of the insects. I analyze the reflection coefficient in this case. Of course, we can measure also the transmission coefficient. The model is basically the same. The only difference is that in this case, we have also another error circuit. One is before and the other is after the device under test. And in this case, the total circuit is a bit more complex. This is the full scheme, and this S11, S22, S12, S21 is the device under test. This is the error circuit before, and this is the error circuit after, and E are the error parameters. Of course, before we have ED, ES, ER, we know these parameters. After we have other two parameters, EL and ET. So in this case, we have a total of 5, to tell the truth, 6 parameters. Why? Because we have another parameters, EX. If you see this parameter EX, skip the device under test, and it models some mutual coupling that we can have in the inner circuits of the vector network analyzer, for example. And so this signal completely skip the device under test. So at the end, we have 6 error parameters, and these are the transmission, the reflection and transmission coefficient as function of the error parameters. And what is interesting in this case is that, for example, the reflection coefficient is not that we measure, that the vector network analyzer really measure, is not only a function of the reflection coefficient of the device, but also is a function of the transmission coefficient. Why? Because part of the signal is able to go through the device, it's reflected, and so it comes again here. And what we measure here is something that is not related only on this reflection coefficient, but also on what happens here. And this is the same for the transmission coefficient. The transmission coefficient is not only a function of S21. S21 is the transmission coefficient that we would like to know, but is also a function of all these other quantities, and in particular also on the reflection coefficient of the port 1 and reflection coefficient of the port 2. This means that when we measure reflection and transmission coefficient with VNA, what we have is something quite complex. The idea again is to use known loads to estimate all these error quantities, and then from these error quantities we invert the relationship in order to obtain S11 from the measured data and S12 or S21 from the transmission data. So the calibration process is basically this. We estimate, we characterize the equivalent error device between the real section of measurements and the section where we have the device under test. And when we invert the relationship, what does it mean? It means that this is a very, very critical, let us say, point. This means that if we make measurement in in the calibration, instead of improving the measurements, we add errors. And also, after measuring these error quantities, we must be sure that these quantities do not change. It means that if we move a cable, for example, we change the error parameters, we add errors instead of subtracting errors. So calibration is very good, but if it's not properly done, it can be very, very dangerous, let us say. Of course, calibration depends on the specific measurement, on specific device. For example, we have calibration optimized for microstrips. This is an example of the measurements that we did with the help of Antonio, and of course we did it at the microwave laboratory, and some of them know this device very well. And in this case, we used a calibration method that was, let us say, optimized for this kind of device. Just in order to conclude, microwave measurements are extremely important for analysis and synthesis of objects. We made a large research on materials, special materials, also using nanomaterials embedded. This is just an example. This is a lightning strike on airplane. And in this case, we need, let us say, some special materials, very, very high conductivity. The nanomaterials can help in this. What we, at the end, what we need is not only to know the permittivity of the material of this material, but we need to know the permittivity of many other materials that are used with this material, because at the end what is important is how this material works with the other materials. This is, for example, a T-join. In this case, we have many different materials, some of them quite special, the other are quite standard. And what is interesting is to model all these materials in order to understand what happens when they work together. And this is an example of a lightning strike. And in this case, we, for example, we reconstruct the current, the surface current during the lightning strike, and we can see this quite complex, let us say, response that depends on the specific material, specific permittivity and conductivity of the materials involved. So, well, this concludes my presentation. This is a very short introduction to error in vector network analyzer, but the message that I would like to leave is that we have a lot of standard method that works well. First of all, we must pay huge attention at the calibration step. We must sure that nothing changes, temperature, position of the cables, and so on, after doing the calibration. Otherwise, we add errors. We do not subtract errors. And in many cases, if we have a bit of time, we can sit down and we can think about some special, let us say, calibration techniques that could be more suited to our problem. Okay, thank you very much. And our question